Alright, hello everyone. So, I'm creating these asynchronous videos in order to help you self-study modern physics. These videos will help you conceptually review all of the main topics in modern physics by discovering the main ideas of modern physics through the use of historic experiments and the analysis of those experiments. So, this asynchronous unit is going to be broken up into, I believe, 6 chapters, although one of them is extremely short. And each one of them is going to help us dig deeper into the main effects of what is known as quantum mechanics. So, today we're going to actually be looking at this first topic called quantum optics, which is the photoelectric, which is observations about the photoelectric effect. All right. So I want you to bear in mind you do not need to actually memorize anything for this topic. So more or less, the historical names and the years provided are not actually important. Some of the experiments are things that you should actually bear in mind because those are the experiments that helped us discover a lot of different things about the microscopic structure of materials. So the first chapter that we're going to start with is known as the photoelectric effect. And the goal of this, and this is going to be a shout out to Matt Lindley, but the goal, he asked the question of what is the point of learning about this photoelectric experiment. And the purpose of this very first experiment is that this is the observation that scientists had actually made in the late 1800s that started making them question what they actually knew about the world, because classical physics was dictated by Newton's laws and a lot of study about electromagnetic waves up to this point, and they actually thought they figured out most different phenomena in the world by that point. However, the photoelectric experiment was the first time our classical models began making incorrect predictions. So I'm going to now show you the very first photoelectric effect experiment. So if you guys check out this video, we're going to play it right over here. In this video, we have an electroscope and a negatively charged object. Because we're touching the electroscope directly with a negatively charged object, this electroscope is going to now take the negative charges and spread it out throughout the entire metal device. This entire device that you see right here with my mouse cursor is made out of metal. Visible light didn't seem to do anything, but now that she's shining ultraviolet light onto the metal, we could see the electroscope seems to be returning back to a neutral state. The only reason why, once again, this stick will repel away is if the entire stick right here becomes the same charge. So we just saw a positively charged stick. Because the stick is positively charged, conduction tells us that the positive charges would actually spread throughout this device, and this is why this device is going to actually show us that the swinging metal rod is going to swing away from the black metal rod, right? And likewise, when we had negatives, the negatives would have spread via conduction. Conduction is, once again, when you share a conductor shares the same charge as a charged object that touches it. So if you're wondering, protons don't move, so how did this happen? It's because when we draw charge diagrams, the positive charges simply represent the direction that the areas that have a lack of electrons. Right? So we can see with a positively charged electroscope now, visible light still doesn't seem to do anything. And now over here with the UV light, we could see it also doesn't seem to do anything. So scientists concluded from this photoelectric effect that something about UV lights seems to be causing the electrons to escape, electrons to shoot out from the metals in some way, shape, or form. So that is what the photoelectric effect is called. It's a discharge of electrons, of negatively charged particles, due to certain types of light. So scientists wondered what aspect of the light is actually causing this. They wanted to make predictions using their current 1800s wave model. All right. So a reminder of what the wave model is. The wave model is essentially when we have a vibrating, right? It's when we have vibrating electric fields. So it is going to be a measurement of the E field at different locations in space, and they thought that, once again, that light at this point was simply some sort of vibrating field, so that the different spots in space, all right, would actually be fluctuating in value with their E field, and through Lenz's law, it would cause the magnetic field to fluctuate, which then induces another fluctuation in the E field, and it will repeat itself, right? So the amplitude of this wave that we see right here is actually what is the total amount of energy, the total amount of energy stored inside the light wave. So scientists wanted to figure out, why is it that the visible light didn't seem to do anything? Could it be that they just needed a more intense, brighter light? So we are going to try testing this out in the photoelectric effect experiment ourselves. So if you check out this next slide, right over here, we could play around with the simulator. So over here, this is known as a photoelectric effect simulator, and there are a few things that we could actually do. So I'm going to show just the highest energy electrons, because for simplicity's sake, we could then focus on fewer electrons in this experiment. And if you take a look right now, the intensity is showing us how much energy is being stored inside this wave right now. Right now, the light is off, and depending on how strong we want to make the light, we can see more electrons seem to shoot out. So this is a vacuum tube, all right? So what we have here is a metal plate on the left. We have another metal plate on the right, and the battery right now is acting like a wire because it has no voltage, no EMF, right? We could see this ammeter reading a current as the electrons are hitting the opposite side, and then as it gets to the opposite side, it's going to redistribute to the original side. So as the electrons are completing the circuit, we could actually see that there's going to be a measured current. As we increase the intensity, you could see that the total amount of current seems to increase, right? We have more electrons that are now able to make it across. However, if we notice, nothing actually changed about the electron speed. And if I decrease the intensity to 0, we have 0 current. So now let's actually check out what the battery does in this experiment. So I'm going to turn back my light intensity to 50%. And we can see electrons making their way across. All right, I'm going to zoom in on this graph a little bit so we could actually see what's going on. And as I make this side become more and more positive, if you look, you can see these little red positive charges being marked on the right side. And it's because, once again, these conductive wires are going to match the V fields of the battery. So the battery now has a difference in V field from left to right of 5.4 volts. And therefore, the right side is going to match the positive V value over here. And this side, if you see, there are little negative symbols right here on the left. And this is going to actually match the V field of the left side of the battery. So since this is negatively charged, electrons that escape are now accelerating. Notice how the speed of the electrons is getting faster and faster as it gets pulled to the right. This is because these are parallel plates with an electric field that is pointing, that is going to point from the positive side to the negative side, and electrons like rolling uphill. So because of this constant electric force by the field between these plates, the electrons are going to get pushed rightwards, opposite the direction of the electric field. If you need a review on the electric field, we could talk about that later. But for right now, just realize that there is an electric field between these two plates, and the electrons are getting pulled towards the positive and repelled from the negative side. Now, what I'm going to, if we look, we're not actually increasing how much current there is in this experiment. We're just increasing the speed of the electrons as they move across. Let's see what happens when we actually move the battery in the opposite direction. Now we can see the current has become 0, right? And the reason why the current is becoming 0 is because we've changed the locations of the positives and negatives. So on this side now we have negative charges. On this side we have the positive charges, all right? And this is because this is the positive terminal of the battery and the negative terminal of the battery. So the wires are going to match the V field values of the EMF source, in this case the battery. So the electrons are getting repelled away from this side. Because the electrons are getting repelled away, it's going to lose the kinetic energy that the light has given it. And now these electrons are getting slower as it tries to get to the other plate, and this is called a stopping potential. This is because the V field value of this battery, right, Vstop, the voltage of this battery, where voltage is the difference in V field, we could call one side 0V, the other would have to be the difference in the V field, so we have a difference of 0.8 volts right here. So Vstop would be the difference in the V fields from the two terminal ends of the battery, and it's causing these electrons to fully lose its kinetic energy by converting the kinetic energy over here, turning into electric potential energy, UQ. And just to remind you of how V field relates to UQ, V field is a ratio of joules of energy per unit charge. So V, the voltage, so the difference in the V field times the charge of the electron would be the total amount of electric potential energy that's being stored up here, if you needed a brief review. Right? So now what we are noticing is that all this kinetic energy gained from the light seems to be turning into electric energy here. So this is how scientists actually measured the total amount of energy the light was providing. They could just set up this EMF source in a way that would stop the electrons, and then they'd have a very easy way to calculate just how much energy was stored in the system of the electrons and light. So let's check out what happens as I increase intensity here. So the traditional EM model said that as we increase intensity, we're increasing the amplitude of those vibrations, right? So we're increasing the amplitude of the electric field vibrations, and as we make the electric field vibrations stronger, it should be able to exert a force on the electrons and protons inside the atomic structure here and cause the electrons to eventually pop out. Let's see if that actually happens. I'm going to increase the intensity here, but we could see there is still no current. So we are not actually adding any energy via intensity. The increase in amplitude of our electromagnetic wave, so if this was our electromagnetic wave at 50% intensity, and this is our electromagnetic wave at double that, with double the amplitude in our wave, we could actually see there is no increase in the amount of electrons being ejected. So this is where scientists began to wonder what actually is light, because if energy isn't stored inside the amplitude of the vibrating electric field, then why are these electrons actually gaining energy? The next thing that they began to play with was frequency. So check out the following. All right, if we actually increase the frequency, decrease the frequency by going to larger wavelengths, we'll notice that no electrons escape anymore. So something about the frequency is affecting the amount of energy the electrons are getting. So this is not enough energy to actually kick out any electrons. Meanwhile, if we go to high frequencies like ultraviolet, we could actually see that the electrons are getting kicked out. And now if I go to even higher ultraviolet speeds, we could see that the electrons are getting kicked out with even more kinetic energy than before. So we could see how much energy is stored here by trying to find a stopping potential. And if you look, we're storing a lot more electric energy inside this field. We have to actually set the battery to a much higher voltage value in order to actually find the stopping potential of the electrons. So something about frequency, high frequency, once again, this is the high frequency side of the spectrum. Higher frequency means a lower wavelength due to our wavelength equation. Wavelength equals the velocity in the medium divided by frequency, right? So a higher frequency wavelength means a shorter wavelength. So that's why you actually see 204 nanometers. It's becoming, with more frequency in UV, we have a smaller wavelength. And scientists wanted to figure out, why is it that more frequency resulted in more energy being provided by the light source? All right, so here we go. Let's go back to the slides. All right, so we wanted to double check if we understand the simulator, and at this point, it's important for you to try these questions on your own. So if you'd like to pause right now, feel free, but I'm going to explain these if you chose to continue listening. So UV light shining on the cathode. All right, the cathode is the metal the metal that the light was being shined on. All right, it's usually known as the side that's connected to the negative terminal of a EMF source, but as you saw, we could actually flip our battery source to find the stopping potential. But all you have to know, therefore, is the cathode is the side that the light is shining on. The anode is the side that the electrons were hitting. All right, so when UV light shines on a cathode, how could UV light actually cause a current? So from our EM model, I'm going to switch screens right now. We could actually see that in a crystal lattice structure, what we actually have is protons, right, being surrounded by these electrons. Right. And the protons are kind of glued together. So if this was one side of our metal, this is the atomic view of what's going on in this experiment. This is the other side. Let's say that the light was shining on the metal, the left side of the metal. What would happen is that, once again, light is a vibrating electric field. So because it's a vibrating electric field, it's going to be able to exert forces to the left and forces to the right. So be pulling the electron left, then right, left, then right. And sometimes, maybe if it's at the right spot, because these particles are always vibrating, we learned from kinetic molecular theory that particles are always constantly moving around. If this vibration is able to become large enough, perhaps it'll bounce into one of the neighboring particles, and then the electron is able to actually leave. So that was the initial idea behind the EM classical wave model. Perhaps it's the vibrations caused by the fluctuating E field that ended up pulling electrons out. And this would only make sense if increasing that amplitude of the E field, right, resulted in a larger force on the electrons. So this was what they believed happened, but we actually saw that this didn't seem to match up as we increased intensity. Electrons wouldn't just escape if they were, and more current wouldn't develop if we didn't have the right frequency of light. So it wasn't amplitude that actually mattered. Now let's answer part B. When the battery is replaced with a wire, the UV light shines on the cathode. The ammeter registers a small current. So what we actually saw here is that, all right, what they're basically saying here is that we can see that there's a current, and if we change it to a wire, we'll still have the same current because the battery just causes the acceleration of the electrons, right? And now going forward, if we reverse the polarity, can we explain why there is a stopping potential? We already explained that in the earlier part of the video. So then I'm just going to keep going I believe we are already explained about light intensity and why that was a little bit strange, and how light intensity did not affect stopping potential, but color does. So it seems like the energy in light depends on frequency. I apologize, these are the slides that I was actually taking a look at. So we just went through A, B, and C, and now we are on parts A and B of this second set of questions, and this brings us to the very last question over here. We also noticed that visible light was unable to discharge the negative electroscope. So the intensity of light did not seem to actually help. We could take visible light and we can make it as intense or low intensity as we want, but all these forms of visible light, if you take a look right over here, seems like this allows for electrons to still escape, but once we get to other forms of visible light, no electrons would escape anymore, no matter how intense we try to make that light. All right. Meanwhile, very, very low intensity light, such as low intensity, high frequency light, would cause some electron ejection. All right. So, yep, you could still see some electron ejection happening even with low intensity. So, our current wave model is unable to explain that. All right. So if you take a look at these graphs, these were the graphs that we actually saw earlier in the simulator. I'm not going to go back into each one of these except for part E. If you take a look at part E, we could actually see that as the frequency of light increases, so this would be towards the seems like my face is slightly in the way. As the frequency of light increases on the bottom right, you could actually see that the stopping potential would have to become larger and larger, meaning there is more energy being stored inside the electric field. So they were able to actually see that kinetic energy that the light gave the electrons became electric potential energy. And as light provided more kinetic energy to the electrons, they were able to measure that with the stopping potential, and we saw that the total amount of energy provided was getting larger. All right, let's continue going forward. All right, so I don't want the video to get too long, so I'm going to now just briefly review the bar chart. So if you look at this bar chart model, what we knew is that there is going to be the attraction, as we talked about earlier, between electrons with the positive nuclei. Right? Attractive energies are negative. We are going to review that in a moment. So if you'd like, please skip to the next part of the video if you need to have a better explanation of that. Now, if we go back to the bar chart, we could actually see that this negative electric potential energy, well, it seems like the light has to provide enough energy to kick out an electron. We could see that once again, this is a conservation bar chart. The beginning energies plus the changes from something external. So our system would be the proton and electrons right over here. The light over here would be the external source, and it provides the electrons kinetic energy, right? And they originally believed that in the wave model, this light energy over here should have been dependent on the total strength of the E field vibrations, or the amplitude of that E field wave graph we saw earlier. So since that didn't seem to work, we need to actually devise what's called a new model. So let's move forward. If you needed a review on negative electric potential energy, this is going to be your quick review over there. So the way to remember this is for repelling objects. Let's think about what happens to the electric potential energy of repelling objects. We store more energy in our repelling objects as we squish them together. Meanwhile, for attractive objects, we store more energy in attractive objects as we pull them apart. All right. So writing both of those patterns down later on, we want to actually create a mathematical model that's able to actually describe both of these. So at infinite distance away, we know that both the repulsive interaction and the attractive interaction cease. So we are going to pick a reference frame. Let's pick infinitely far away as a reference frame, and then we could actually create an explanation, a mathematical model for what the UQ amounts were. So just one brief review before we go on to talking about that mathematical model is the difference between a scalar quantity and a vector quantity. All right. So a scalar quantity is going to actually be when on a number line, lower numbers simply mean lower. This is similar to things like temperature. So if you take a look at the temperature of an object, we could actually see over here 5 degrees Celsius and negative 5 degrees Celsius. Well, negative 5 degrees Celsius is simply a lower temperature than 5 degrees Celsius. However, this is different from vectors because 5 meters per second negative and positive 5 meters per second positive is just the directions a object would be traveling. So we are talking about scalar quantities, which is why we need a reference frame so that we could just state our numbers and recognize that lower numbers, such as more negative numbers, are actually just smaller amounts. All right, so if you're okay with scalars, let's move on to the next slide. And we could now see that our two patterns for repelling objects is shown right up here, for attracting objects is shown right down here, and at infinite distance away, so at very high amounts of distance, we could see that the total interaction gets close to 0. Now, what did we say as we took repelling objects and pushed them closer together? Well, the UQ value should become higher, right? Meanwhile, for repelling objects, when we pull them far away, they're no longer interacting, so the starting UQ at when R is infinitely far away is 0. But when we let them come closer together, they're actually going to increase in kinetic energy, meaning they're losing UQ. So as the UQ decreases and we let the attracting blocks come closer together, that potential energy is going to turn into something else. And the way we could show this is by, once again, picking infinitely far away as 0 UQ, and then this UQ is going to become smaller by turning into other sources of energy, and the only way to do this is if we make attraction described by negative amounts of energy. All right, so this simply means if you see negative energy, just remember that it's describing an attractive situation. So it would be a circumstance in which we have two objects bound together. All right, moving on. All right, so how does this apply to the photoelectric effect? Ultimately, we want to know the negative UQ is once again relating to how these electrons are bound to the nucleus. All right, so this is so if we keep going, if we're able to actually provide energy from the light, so for example, when that light shines here, if it's able to actually provide, all right, this is my flashlight. Right, when it's shining energy, if it's able to provide these electrons enough energy, some of these electrons would be able to escape. All right, so we just need more electric energy, more energy from the light than the negative electric potential energy of UQ in order for electrons to escape with some kinetic energy. All right, so once again, as a refresher, negative UQ over here. If we're able to provide enough light energy, then whatever remains is going to turn into that electron's kinetic energy. So it seems like we have a way of describing the photoelectric effect and why light is able to actually kick out electrons. But we don't understand why the amplitude of that light is not affecting the total amount of energy provided by the light. So let's now explore why frequency might actually have an effect. All right, I believe I'm going to make, all right, so you know what? I'm going to make this the first video because this video is already going on pretty long, and I believe we reviewed most of this in class. So This first video went over the wave model and how the wave model failed to actually explain the photoelectric effect due to, once again, the amplitude of the wave not actually relating directly to how much energy these electrons were being provided. All right, so we could actually take a look at the velocity of the electrons. As a recap, you could see that these electrons still move with the exact same kinetic energy the entire time, irregardless of what the amplitude is. So it seems like intensity just relates to how many electrons are being ejected. Alright, on the next video, we're going to invent a new model to explain what is happening in this experiment.